Alright kids, today we're going to go through and focus on how to name, draw, come up with formulas, and basically do all of Unit 3, and we're going to have a whole bunch of different possibilities here. There'll be the possibilities of ionic bonds, and the ionics will also have transition metals in there, which are a different variation. We'll have covalent bonds, and then we'll also have polyatomics. If you happen to be in one of the classes that does not require the knowledge of polyatomics, obviously if we get to one of those examples, go ahead and skip it. Anyways, as a prefix to all this, I guess the first question that you should ask yourself if given any question at all, any problem, is basically, is there a polyatomic? Okay. If yes, then you go through and use the polyatomic chart. Okay. And we will provide a chart for you. And there's only about 7 or 8 of them that you need to know. The other option is no. Okay. Now, maybe you need to know what a polyatomic is, and basically if you see more than 2 capital letters in your problem, it's going to be a polyatomic, and we'll look at that in a little bit. Obviously, if it's a no, it's going to be a simple ionic or covalent. Okay. So your next question is going to be, is there a metal? And the metal is going to open yourself up to yes, which means we're dealing with ionic bonds. You're going to use arrows to actually draw them out. We're going to use crisscrossing, and what that means is you got to find the oxidation number in crisscross. And we'll also go through and use no prefixes, and we'll use Roman numerals to indicate the oxidation number of a transition metal if we find one. So that's for ionic. Our other set's covalent. Okay, so if there's not a metal, we go to covalent, okay? And basically those use lines to show bonding. We don't crisscross at all, and we're using Greek prefixes. So, without further ado, we are going to rock through some problems really quickly. And so we'll start off with our first one. SrCl2. My first thought should be, is there a polyatomic? Well, I only see 1 capital letter, so no, those are out of the question. So I look at this guy, Sr. I know that Sr happens to be a metal, an alkaline earth metal, so I know this is going to be ionic. Okay. My formula is obviously SrCl2, and so naming this thing being ionic, it's going to end up being strontium chloride. I do not have to worry about the number 2 being ionic. I don't worry about the numbers. In terms of the drawing, I know I've got a singular Sr with 2 valence electrons, and then 2 Cl's. And each Cl is going to end up having 7 valence electrons. And again, if you get to the point where you're looking at stuff and it doesn't make sense at all, pause, go back, try it again. Until you go through and completely understand these, you can go back. All right. Our second set, we've got K3PO4. So looking at this whole thing right away, my first thought process should be PO4 looks like one of these polyatomics up here, specifically phosphate. We know it's got a -3 charge, and that'll come into play. So in terms of the actual setup over here, I would call this a polyatomic. Your formula, again, is just going to be this guy, so I don't have to go through and name it out. But in terms of the name, I know that we're going to name it just like ionic, so I'm going to start off with potassium. And with polyatomics, I never change the name, so it's going to be potassium phosphate. Okay. And in terms of drawings, you do not have to be able to draw this stuff, but essentially what's going on is I'm going to have a simple PO4 somewhere in here, and then you're going to have 3 extra electrons that want to be that are lonely, and you're going to have a potassium giving an electron to each set. And that's basically the kind of idea of what this is. You've got 3 potassiums and 1 PO4. Again, don't need to have to draw this. All you got to be able to do for polyatomics, formula and name. Moving on to our next set, we've got Fe2O. So we go through and look at this. Is there a polyatomic? Iron's not, oxygen isn't, so cross off that guy. Is it ionic or is it covalent? I know that happens to be a metal, so we're an ionic, but there's a big key with a transition. So that's a big key. I know I'm going to use my transition metal, so that's a really big deal here. So our formula here is simply going to be this guy. I don't have to worry about formula again. But the name, we've got to go through and figure out what's happening here. So I'm going to uncrisscross this to figure out my name. So I go with Fe and O. I know this 2 comes up top to become my O, minus 2. And there's an invisible 1 here that's going to come up top. So Fe plus 1. So when I set up the entire name, is going to end up being iron 1 oxide. Okay? And in terms of drawing this, I'm going to end up with 2 irons, because I told you I have 2 irons, and 1 oxygen. And each oxygen has 6 valence electrons. Each iron we looked at has 1 valence electron. We just told you that when we found the oxidation number. So each iron gives a valence electron to oxygen. Starting out our next one, we've got CH4. So again, my first question, is there a polyatomic? Not at all. Cross those off. There's only C and an H. Is there a metal? No, there's not a metal, so we know it's not ionic. We're going to end up with a covalent here. Again, we know the formula because all I keep giving you is formulas. But naming will be a little more challenging. We use prefixes for everything unless the very first one is a 1. So we're going to end up with carbon, because there's only 1 and we're not using a prefix. And then tetrahydride, 4 hydrogens. And then in terms of your drawing, we've got 2 sets. I end up with a carbon in the middle. It's got 4 valence electrons and a hydrogen kind of winging each side. And we simply circle electrons so that they are paired up. And that means your final drawing is going to end up looking like this guy, with a line coming off each side and an H attaching to each line. The carbon has 8 valence electrons. Each hydrogen has 2 because it's touching a single line. Moving on to our next one, magnesium nitride. Ooh, all right, so we finally get a name. That's where this guy goes. I know right away that magnesium's a metal, but nitride, is that a polyatomic? I don't see nitride on here, so we're just going to stick with straight up ionic. I know my formula, magnesium is a plus 2, and I know that nitride is going to end up being a minus 3. So when I draw this whole thing out, I'm crisscrossing, and I end up with an Mg3N2. So in terms of my drawing, this is going to be as complex as we can get. I'm going to end up with 3 magnesiums, and I'm going to end up with 2 nitrogens. Each nitrogen has 5 valence electrons. Each magnesium has 1, 2, 1, 2, 1, 2. And so we'll color code these. The magnesium's giving here, and magnesium's giving here. The magnesium's giving here, and the magnesium's giving here. And then this magnesium is giving here and here. If you can get this, that's as complex a drawing as we are realistically going to have. Working our way down to the next one. I've got Cl2. Now this one's kind of, I hate to say, a little tricky. We've got a covalent bond here because, again, this is simply a nonmetal, but there is something that you should, when you see chlorine, be aware of. This is going to be a diatomic. And this is one of our 7 that bonds to only itself. Remember, if you can't remember our 7 diatomics, we've got Br, I, N, Cl, H, O, and F, our Brinkelhoff. Please remember those 7. Those are the diatomic molecules. Now, in terms of the formula, you got that guy, but the name is really, really kind of important here. Being that this is Cl, we're not actually naming covalent bonds. We're naming this simply a chlorine molecule, because this is simply one molecule of chlorine. All right? There's 2 chlorine atoms bonded together to form one diatomic molecule. In terms of your drawing, I get a Cl, I get a Cl, 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. That guy gets a circle, which means we're left with chlorine, chlorine, there's a line, and again valence electrons to make the whole thing happy in terms of stable outer valence shells. Moving on to the 8th one, I've got calcium nitrate. Alright, so let's work our way through this. Calcium, I know, is a metal, so we're talking ionic. But nitrate, nitrate looked weird. It didn't end in IDE. That should have been our first clue right there, and we know it's going to be an NO3. Wow, did not mean for that to happen. So we've got NO3. So realistically, this one's going to get fun. We know we're dealing with, yes, it's going to ionically bond, but we're talking about a polyatomic. And remember, a polyatomic is going to be a covalently bonded thing, a covalently bonded molecule, and this nitrate is going to be covalently bonded, essentially NO3 covalently bonded together, but it's going to ionically bond to this calcium atom, or ion. Okay. So in terms of our formula, we start getting a little fun. Calcium, we know, is going to be a nice little Ca plus 2, and I know nitrate is going to be NO3, and I know it's got this -1 charge. Okay, again, if it's a polyatomic, let the chart tell you everything. It does all the work for you. Okay, so from here, all we're doing is we are crisscrossing. This 2 comes down to the outside of the parentheses. This 1 is coming down to the right of the calcium, so I'll end up with a Ca invisible 1, and then an NO3 and the parentheses with a 2 outside it. And so again, I'm getting rid of that 1, and it turns into CaNO2. And so again, what this basically looks like, and you do not have to be able to draw this, but I'm going to have one calcium that has 2 valence electrons. I'm going to have an NO3 over here. I'm going to have an NO3 over here, and that's basically going to give a electron to each of those. All right, that's essentially, conceptually, what you are trying to do with these polyatomic ions. Covalently bonded thing, ionically bonded to calcium. Okay. Moving on to number 9, I've got Ni2O3. This guy gets a little tricky. All right, so is there a polyatomic? No, I only see 2 capital letters, so I know this guy, ignore it. In terms of the Ni2, I know the Ni, nickel, happens to be a metal, so we're dealing with ionic, but I know this nickel happens to be a transition metal, so we're talking transition. Alright, so that makes our life a little more interesting. The formula is that guy. The name, in order to find the name, I know that this is going to end up being nickel. I know that this is going to have something in parentheses, and then we're oxide. Okay, now the question is, what goes in parentheses? I'm trying to find the oxidation number for nickel. And in order to do that, I'm going to take this number here and shift it up top. I'm trying to figure out what's the charge of nickel that I would need 2 nickels to balance out my 3 oxygens that are -2. -2 times 3 gives us 6. Something times 2 will give us 6. So this is going to end up being our +3. So we're going to end up having 1, 2, 3 in terms of the nickel 3 oxide. And then the drawing, again, this is one of those really crazy ones. I'm going to have a nickel and a nickel because I said Ni2. And I'm going to have 3 oxygens. Nickel has, as we said, 3 valence electrons, so 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Wow, didn't want that one. We'll hit back real quick. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we are, again, 2 go here, 2 go here, and 2 go here. And I got really quick and dirty with that one just because I'm trying to get through to a couple more. We got about 30 seconds left. Our last polyatomic here, ammonium carbonate. I know ammonium is going to end up being this guy, and carbonate is going to be this guy. So we're getting really, really fun. So this is going to be our polyatomic. In terms of the formula, I'm going to end up with NH4, and I know that this is a +1, and carbonate is a CO3, and this is going to be a -2. So what we're doing is we are shifting down and shifting down, and I get an NH4 2, and CO3 right there.